Hello there and welcome to Cosmos for Sleep. Tonight we're drifting through the radiant lives and quiet deaths of stars, exploring their hidden facts and profound cosmic influence. If these calm, curious explorations help you unwind, consider liking and subscribing to the channel. It helps others find their way here too. For now, just breathe. Let your eyes grow heavy. And let's begin. The carbon in your body, the oxygen you breathe, the iron in your blood, all were forged inside stars. These fundamental elements, essential for life as we know it, did not exist in the early universe. They were created through the immense pressures and temperatures within stellar cores, a process known as nuclear fusion. Every atom heavier than hydrogen and helium in your very being, and indeed in everything around you, began its journey within the heart of a star that lived and died long ago. We are, quite literally, made of stardust, connected to the cosmos in a profound and elemental way. Indeed, this cosmic connection runs deep, as stars truly are the universe's ultimate alchemists, engaging in a continuous process of transformation that underpins all existence. These magnificent celestial bodies function as giant cosmic ovens, tirelessly working to fuse lighter elements into heavier ones within their fiery hearts. From the moment of their luminous birth, stars embark upon a remarkable journey of creation, taking the simplest and most abundant building blocks of the universe, primarily hydrogen and helium, and transforming them into the vast array of elements we encounter throughout the cosmos. This gentle alchemical process is known as nuclear fusion, a quiet, steady force that powers their immense luminosity and sustains their brilliance for billions of years. Deep within a star's incandescent core, under the almost unimaginable pressure and heat that exists there, atomic nuclei are compelled to merge together, forming new, more complex elements. This is the fundamental mechanism through which the universe creates carbon, that versatile element forming the very backbone of all known life, the oxygen that flows through our atmosphere and sustains our breath, the iron within our blood cells, and countless other intricate elements that go on to compose planets, moons, asteroids, and indeed, everything we perceive around us. Without these stellar furnaces, silently operating across the vastness of space, the cosmos would remain a much simpler and far less interesting place, composed almost entirely of the lightest gases, utterly devoid of the rich diversity of matter and the intricate chemical structures we observe and experience today. The quiet hum of fusion within each star is a continuous and profound act of cosmic manufacturing, steadily building the intricate chemical tapestry of existence, piece by gentle piece, over unimaginable spans of time. It is a testament to the universe's capacity for self-creation, a quiet internal forging of the raw materials for all future wonders, forming the very essence of what we are. Long before stars like our familiar sun began to grace the night sky with their comforting glow, the universe bore witness to the birth of its very first luminous giants. These primordial objects, known to astronomers as population 3 stars, were, in their essence, unlike anything we observe in the cosmos today. They emerged from the pristine, unblemished gases left over from the Big Bang itself, a universe then composed almost exclusively of hydrogen and helium, and thus containing virtually no heavy elements. Their initial composition was a pure and simple blend of these two lightest elements, the only raw materials available in that nascent early era. Without the presence of heavier elements, which typically act as crucial coolants in the formation and evolution of modern stars, these population 3 stars grew to absolutely extraordinary sizes. Scientists believe they were hundreds of times more massive than our modest sun, perhaps even reaching masses equivalent to several hundred suns, making them truly colossal. Such immense size meant they consumed their nuclear fuel at an astonishingly rapid rate, shining with a fiery brilliance that was truly spectacular, radiating light 1,000,000 times brighter than our own steady sun. Their lives, though undeniably glorious and impactful, were remarkably fleeting by cosmic standards, lasting only a few short million years before they gracefully reached their majestic end. These colossal, luminous pioneers were the very first to illuminate the universe, piercing the long era of cosmic darkness and initiating the crucial process of enriching the cosmos with the very first heavy elements. Their brief but intensely powerful existence laid the foundational chemistry for all subsequent generations of stars, galaxies, and eventually the complex structures that would emerge. Their light is gone now, but their fingerprints remain, subtle and quiet, in the chemical makeup of the ancient gas clouds and the underlying structure of the early cosmos, a silent legacy that continues to resonate through time, shaping everything that follows. All stars, without a single exception, including our familiar and life-giving sun, begin their lives in a remarkably similar, gentle, and profoundly beautiful process. They are born from the slow, elegant collapse of vast, majestic clouds of gas and dust, ethereal structures known to astronomers as nebulae. These nebulae are, in essence, the universe's stellar nurseries, quiescent and often breathtakingly beautiful regions where the raw materials for new stars quietly gather and coalesce over eons. Within these immense, sprawling clouds, subtle gravitational instabilities begin to exert their gentle pull, drawing material inward. Over vast spans of cosmic time, tiny pockets of gas and dust slowly, almost imperceptibly, begin to coalesce, growing denser and warmer as more particles are drawn into their gravitational embrace. As more and more material accumulates, the gravitational pull at the center intensifies steadily, causing the entire cloud to shrink and, in many cases, to begin a slow, graceful rotation. This slow, inward collapse continues for many millions of years, transforming a diffuse cold cloud into a dense, intensely hot, and rapidly rotating core, often referred to as a protostar. Eventually, the pressure and temperature at the very heart of this collapsing mass become so extreme, so immense, that nuclear fusion ignites with a gentle, yet profound, burst of internal radiance. This moment marks the true birth of a star as it settles into a stable phase of its life, balancing the inward pull of gravity with the outward pressure from its fusion reactions. But not all stellar journeys lead to such a quiet, predictable end. For the most massive stars, their lives conclude in spectacles of extreme physics, leaving behind some of the universe's most astonishing remnants. Consider the neutron star, a silent, dense relic born from the heart of a massive star that has concluded its life in a grand, final burst of radiance. These incredibly compact objects represent a state of matter unlike anything we typically encounter. Imagine compressing the entire mass of our Sun, a star hundreds of thousands of times wider than Earth, into a sphere only about 20 kilometers across. The result is a neutron star, where gravity has crushed atoms so completely that protons and electrons merge, forming an almost pure sea of neutrons. This extreme compression leads to an unimaginable density. To give a sense of this, a mere single teaspoon of material taken from the core of a neutron star would possess a weight equivalent to billions of tons. To put that into perspective, it would outweigh Mount Everest many times over, all contained within a volume small enough to hold in your hand. This density defies our everyday experience, where even the heaviest materials on Earth feel light by comparison. It is a quiet testament to the immense forces at play during the final moments of a giant star, where matter itself is pushed to its absolute limits, becoming a silent, incredibly heavy core. The very structure of space and time around such an object is gently warped by its profound mass, creating a subtle gravitational well that is almost beyond comprehension. These tiny, city-sized powerhouses are not merely remnants. They are living laboratories of extreme physics, allowing us to glimpse the fundamental nature of matter under conditions that can never be replicated in any terrestrial setting. Their quiet existence speaks volumes about the universe's capacity for transforming the familiar into the truly extraordinary, leaving behind objects that are both immensely heavy and profoundly compact, anchors of gravity in the vast cosmic ocean. Further adding to the extraordinary nature of neutron stars is their incredible rotation. Many of these stellar remnants spin with astonishing speed, a consequence of the conservation of angular momentum as their progenitor stars collapsed. Among them are a particularly fascinating type known as millisecond pulsars. These compact objects can complete hundreds of rotations every single second, often spinning at rates exceeding 700 times per second. To visualize this, consider the speed of a typical kitchen blender blade, which operates at a fraction of this rotational velocity. Now, imagine an entire stellar core, a sphere with the mass of a sun, spinning at such dizzying rates. This rapid rotation creates an almost perfectly precise cosmic clock. As they spin, these pulsars emit beams of radiation from their magnetic poles. When these beams sweep across our line of sight, we detect them as rhythmic pulses of light or radio waves, much like the steady, precise beam from a cosmic lighthouse. These silent, rapid ticks are among the most stable timekeepers in the universe, a continuous, quiet rhythm emanating from the extreme physics of stellar death, providing astronomers with invaluable tools for studying the fabric of space-time itself. The regularity of their celestial beats allows scientists to observe subtle changes in the very fabric of the cosmos, making these fast-spinning stars silent, powerful instruments of discovery. Among the family of neutron stars, there exists an even more exotic and powerful member, the magnetar. These are neutron stars endowed with an unimaginably intense magnetic field, a force so profound it dwarfs anything we can comprehend on Earth. While our planet's magnetic field is strong enough to guide a compass needle, a magnetar's magnetic field can be trillions of times stronger. This colossal magnetic force is so potent that it could, in theory, erase all data from electronic devices thousands of kilometers away, or even distort the very atomic structures of matter in its immediate vicinity. It is a silent, invisible force, yet one of the most extreme phenomena in the cosmos. Scientists believe these incredible magnetic fields are formed during the dramatic collapse of a massive star, when convection and turbulence within the star's rapidly rotating core amplify the magnetic field to these astonishing levels, twisting and knotting the magnetic field lines until they reach an almost inconceivable intensity. The birth of a magnetar can also be linked to some of the universe's most powerful stellar explosions, known as hypernovae. While a typical supernova is a brilliant and awe-inspiring event, a hypernova is an even grander, more energetic spectacle. When a particularly massive star collapses and its core forms a magnetar, the immense energy released by the star's magnetic field as it settles and twists can drive an explosion that far surpasses the luminosity of a standard supernova. These hypernovae, sometimes associated with long-duration gamma-ray bursts, unleash a torrent of high-energy light that can briefly outshine entire galaxies. They are brief, intense bursts of radiance, lasting only a few seconds, yet their light can travel across billions of light-years to reach us, carrying the quiet memory of a star's final, incredibly powerful act, a testament to the colossal forces at play when matter and magnetism reach their ultimate extremes. The sheer outpouring of energy from a hypernova is a quiet reminder of the hidden power contained within the very fabric of space, released in a gentle, yet monumental, cosmic exhalation. These events reshape their galactic neighborhoods, scattering newly forged elements far and wide, gently influencing the birth of future stars and planetary systems with their quiet, radiant legacy. While many massive stars conclude their lives in a magnificent supernova, a brilliant burst of radiance that seeds the universe with new elements, there is a more subtle, yet equally profound pathway to stellar death. For the most exceptionally massive stars, those at the very upper limits of stellar mass, their end can be strangely quiet, devoid of the expected cosmic fireworks. When these colossal stars exhaust their nuclear fuel, their immense gravitational pull becomes overwhelming. Instead of the outer layers being ejected in a grand, luminous explosion, the entire star's core and even its outer layers can collapse inwards so rapidly and completely that gravity triumphs without a visible struggle. the star simply implodes, its matter falling directly into the nascent black hole at its center. This process is known as a direct collapse. In these instances, there is no brilliant flash, no spectacular farewell, just a sudden, silent disappearance from the cosmic stage. Astronomers have, on rare occasions, observed stars that were once clearly visible in the night sky suddenly vanish without a trace, as if their light had simply blinked out. These quiet disappearances serve as a gentle reminder that not all cosmic endings are heralded by dramatic displays of light and sound. Some simply transition into the profound silence and invisibility of a newly formed black hole, a testament to the universe's capacity for both brilliant display and serene, unobserved transformation. They become the quiet, unseen devourers of light and time, leaving behind only a gravitational echo of their former brilliance. Even black holes, those anchors of space-time, are not entirely immune to cosmic motion. While they are often imagined as fixed points of immense gravity, they too can embark on journeys across the galaxy, pushed by the subtle yet powerful ripples of space-time. When two black holes, locked in a graceful cosmic dance, finally merge into a single, more massive black hole, the event sends out powerful gravitational waves. These ripples in space-time, predicted by Albert Einstein and now directly observed, carry away energy from the merging system. However, if the two original black holes are not perfectly symmetrical, or if their spins are misaligned, the emission of these gravitational waves can be uneven. This asymmetry acts like a gentle, subtle recoil, imparting a kick to the newly formed, larger black hole. This gravitational kick, though imperceptible to our senses, can be incredibly powerful, capable of accelerating the merged black hole to speeds of thousands of kilometers per second. Such a rapid acceleration can propel the black hole entirely out of its host galaxy, sending it drifting silently through intergalactic space, a solitary wanderer, forever separated from its cosmic birthplace. Other times, the kick might be less severe, simply altering its orbit within the galaxy, causing it to trace a wide, wandering path among the stars. These kicked black holes are extremely challenging to detect, as they are inherently invisible unless they interact with surrounding gas or stars, creating subtle disturbances that astronomers can painstakingly observe. Nevertheless, scientists believe they exist, quiet travelers pushed by the memory of their own colossal collision, a gentle reminder that even the heaviest and most profound objects in the universe are subject to the subtle forces and elegant dynamics of cosmic motion, never truly still, but always in a state of quiet, ceaseless drift, leaving a silent path through the cosmic tapestry. As we contemplate the profound movements of black holes, it is equally humbling to consider the sheer diversity in the sizes and temperatures of stars themselves, a spectrum that stretches from the truly immense to the barely perceptible, each a unique expression of cosmic physics. Among the most astonishing examples of stellar grandeur is the largest known star, a luminous supergiant designated UY Scuti. Its scale is almost impossible to grasp within our everyday frame of reference. If this colossal star were to be gently placed at the very center of our own solar system, its expansive outer layers would comfortably extend far beyond the orbit of Jupiter, swallowing Mercury, Venus, Earth, and Mars whole. Indeed, its vast diffuse atmosphere would reach out to encompass even the mighty gas giant, Jupiter itself, leaving our familiar planetary orbits deep within its fiery embrace. To travel around its equator at the speed of light, it would take several hours, a testament to its truly unimaginable circumference. UY Scuti is not merely large, it is an object of truly staggering proportions, a testament to the universe's capacity for producing structures on a scale that humbles the human imagination. Its immense size means it sheds vast amounts of material into space, contributing to the rich tapestry of interstellar gas and dust, a silent, continuous exhalation that enriches its cosmic surroundings. This star, glowing quietly in its distant corner of the galaxy, reminds us that our sun, while vital to our existence, is but a modest ember in a cosmos filled with truly gargantuan celestial fires, each a silent monument to the universe's grand scale and diversity. On the opposite end of the stellar size spectrum, we find stars that are barely large enough to qualify as stars at all. The smallest stars known to exist are truly diminutive by cosmic standards, possessing only about 8% of the mass of our Sun. This particular mass threshold is critically important, as it represents the minimum amount of gravitational compression required for a celestial body to ignite and sustain stable nuclear fusion in its core. Below this mass, the core of a protostar simply cannot generate enough pressure and temperature to initiate the fusion of hydrogen into helium. These tiny, low-mass stars are often called red dwarfs, and they burn their nuclear fuel at an incredibly slow and efficient rate. This gentle, measured consumption of hydrogen means they can live for truly immense periods of time, far longer than the current age of the universe itself, quietly glowing with a dim, reddish light for trillions of years. They are the marathon runners of the cosmos, enduring for eons, while more massive stars burn brightly and then fade away. Their quiet, persistent glow is a testament to the universe's efficiency, ensuring that even the most modest accumulations of matter can contribute to the cosmic light show, albeit in a subdued and long-lasting manner. These miniature stellar embers are the most numerous type of star in our galaxy, silent, persistent sentinels scattered throughout the cosmic night, each one a tiny, enduring furnace. Even more remarkably, some stellar remnants can be smaller than planets, presenting a fascinating paradox of cosmic scale. White dwarfs, the final gentle stage in the life cycle of stars like our Sun, offer a prime example of this extreme compression. After a star like our Sun expands into a red giant and then softly sheds its outer layers into space, what remains is its incredibly dense core. This core, now a white dwarf, is typically about the size of Earth, a mere fraction of its former self. Yet, despite its planetary dimensions, a white dwarf retains a substantial portion of its original stellar mass, often equivalent to that of our entire Sun. This means that matter within a white dwarf is incredibly compact, a testament to the immense gravitational forces at play. A single cubic centimeter of white dwarf material could weigh several tons, an astonishing density for an object the size of a world. These quiet, glowing embers no longer undergo nuclear fusion. Instead, they slowly radiate away their leftover heat over billions, even trillions of years, gradually dimming until they become invisible black dwarfs. They are silent, luminous fossils, quiet reminders of a star that once burned brightly, now slowly cooling in the cosmic dark, a planet-sized gem of compressed stellar history. The range of stellar temperatures is equally astonishing, stretching from the scorching infernos of massive blue stars to the barely glowing embers of the coolest celestial bodies. In a truly fascinating discovery, astronomers have identified objects that blur the lines between stars and planets, some of which are so cool that they are barely warmer than Earth's room temperature. These ultra-cool brown dwarfs, often referred to as failed stars, because they lack the sufficient mass to ignite sustained nuclear fusion, emit very little visible light. Their surface temperatures can drop to a mere few hundred degrees Celsius, which, while still hot by terrestrial standards, is incredibly cool for a celestial object. In fact, some of these enigmatic objects are so cool that they are only slightly warmer than a comfortable room on Earth, making them almost too faint to glow in the visible spectrum. We typically detect them through their faint infrared radiation, a subtle warmth that betrays their presence. These quietly glowing celestial bodies challenge our conventional definitions of what constitutes a star, revealing a spectrum of cosmic objects that exist in a transitional state between planet and star. They are silent, dim presences in the galaxy, almost invisible, yet they contribute to the quiet thermal background of the cosmos, a testament to the sheer diversity of celestial forms that can emerge from the universe's vast material. At the other extreme, The universe hosts stars that burn with an almost unimaginable intensity, radiating tremendous amounts of energy. The hottest stars are typically characterized by their striking blue or blue-white coloration. These are often massive young stars, consuming their nuclear fuel at an incredibly fast rate. Their surface temperatures can soar to tens of thousands of degrees Celsius, sometimes even exceeding 50,000 degrees Celsius. This extreme heat causes them to emit light predominantly in the blue and ultraviolet parts of the electromagnetic spectrum, giving them their characteristic hue. Their brilliant, intense glow illuminates vast regions of space, ionizing nearby gas and carving out luminous nebulae. Acting as cosmic beacons in stellar nurseries, these stars live fast and die young, burning through their fuel in a few million years. But during their brief, spectacular lives, they profoundly shape their galactic environments, seeding new generations of stars and planets with their radiant energy. Their silent, intense heat is a driving force in cosmic evolution, a powerful yet gentle sculptor of the interstellar medium. Conversely, the coolest stars in the universe present a much more subdued and tranquil appearance. These stars, often red dwarfs or red giants in their later stages of life, are defined by their distinct red coloration. Their surface temperatures can be remarkably low for a star, sometimes falling to around 2,000 degrees Celsius, while still incredibly hot compared to anything on Earth. This is significantly cooler than our Sun's surface temperature of about 5,500 degrees Celsius. This lower temperature means they emit most of their light in the red and infrared parts of the spectrum, giving them their characteristic deep red glow. Red dwarfs, in particular, are incredibly long-lived, burning their fuel so slowly that they can quietly persist for trillions of years. They are the quiet, enduring embers of the cosmos, providing a steady, gentle warmth to any potential orbiting worlds for eons. Their soft, reddish light is a testament to a slower, more deliberate form of stellar existence, a serene contrast to the fiery intensity of their blue counterparts. Perhaps one of the most immediate and visually striking indicators of a star's fundamental properties is its color. A star's color serves as a silent, immediate indicator of its surface temperature, offering a direct glimpse into its internal dynamics. Blue stars are the hottest, radiating at incredibly high temperatures. Their intense heat causes them to emit light across the electromagnetic spectrum, with a peak in the blue and ultraviolet wavelengths, giving them their brilliant azure or blue-white appearance. Conversely, the coolest stars are red, their lower surface temperatures causing them to emit light primarily, resulting in a deep, warm red hue. Stars like our Sun, which appear yellow-white, fall in between these two extremes, possessing moderate surface temperatures. This gentle color spectrum, from brilliant blue to soft red, is not merely an aesthetic feature of the night sky. It is a fundamental property of stellar physics, reflecting the intricate balance of temperature, mass, and energy within each celestial body. By simply observing a star's color, astronomers can quietly infer a great deal about its nature, its age, and its place in the cosmic tapestry, a silent language spoken across vast distances, allowing us to understand the universe through the gentle hues of its luminous inhabitants. Our own Sun, a familiar and comforting presence in our sky, also has a long and predictable journey ahead, a stellar life cycle that will unfold over billions of years. In the distant future, approximately 5 billion years from now, our Sun will gently begin its transformation, swelling gracefully into a red giant. This serene expansion marks a significant shift in its stellar evolution. Having exhausted the primary hydrogen fuel in its core, the Sun will begin to fuse hydrogen in a shell surrounding its now inert helium core. This change in its internal structure will cause its outer layers to expand dramatically and cool, giving it a distinct reddish hue and an immense size. As it gently expands, its outer atmosphere will gradually encompass the orbits of the innermost planets. Mercury and Venus, closest to the Sun, will be slowly absorbed into its vast, expanding embrace. There is also a possibility that Earth, our homeworld, will find itself enveloped within this grand, evolving star, becoming a part of its outer atmosphere. This is not a violent catastrophe, but rather a slow, majestic transformation, a natural and elegant progression in the life of a star like ours. The Sun will grow to hundreds of times its current diameter, becoming a truly colossal, albeit cooler, star. This future, though distant, is a testament to the quiet, ceaseless change that governs all celestial bodies, a gentle redefinition of our solar system's architecture over an unimaginable timescale. The familiar yellow-white sphere we see today will become a red giant, a beautiful, expanded form, a silent and inevitable chapter in its long cosmic story. This expansion will be a gradual process, taking millions of years, allowing its outer layers to softly reach outward, drawing in the inner worlds with a gentle, inexorable gravitational embrace. The energy that radiates so freely from the Sun's surface, warming our planet and sustaining life, embarks on an incredibly long and intricate journey from its birthplace deep within the Sun's core. Once generated through nuclear fusion, a single photon of light does not simply travel straight to the surface. Instead, it engages in what scientists describe as a random walk, a convoluted path that can take hundreds of thousands of years to complete. The Sun's interior is an incredibly dense environment, a hot, opaque plasma where photons are constantly absorbed and then re-emitted by countless atoms. Each time a photon is absorbed, it is then re-emitted in a completely random direction, causing it to bounce around endlessly within the Sun's radiative zone. This process is repeated countless times, millions upon millions of interactions, before the photon finally manages to escape into the convective zone and then, at last, emerges from the Sun's visible surface, the photosphere. This immense journey through the Sun's interior contrasts sharply with the relatively swift 8 minutes it takes for light to travel from the Sun's surface to Earth. It highlights the profound density and complexity of our star's internal structure, a silent, internal labyrinth where light particles spend eons navigating before they can finally stream out into the vastness of space. This slow, persistent diffusion of energy ensures a steady and stable output, a continuous flow of warmth that has nourished our world for billions of years, a testament to the Sun's quiet, enduring power. The journey of each photon is a silent epic, a long, slow dance through the Sun's fiery depths before it finally bursts forth to touch our world. At the very heart of the Sun, where the magic of stellar creation truly unfolds, lies a region of unimaginable heat and pressure. The Sun's core temperature is an astounding 15 million degrees Celsius. These extreme conditions are precisely what are required to overcome the natural electrical repulsion between atomic nuclei, allowing them to fuse together in the process of nuclear fusion. It is here, in this incandescent furnace, that 4 hydrogen nuclei are gently combined to form a single helium nucleus, releasing a tremendous amount of energy in the process. This energy, in the form of gamma rays and neutrinos, is the ultimate source of all the light and heat that the Sun emits. The core is a dynamic and incredibly active region, a silent powerhouse where the fundamental forces of nature are engaged in a constant, delicate balance. Without this extreme temperature and pressure, the Sun would simply be a large ball of gas, unable to generate its own light and warmth. The quiet intensity of the core is the engine that drives the entire star, a continuous, controlled reaction that has sustained our solar system for billions of years. It is a testament to the universe's ability to create pockets of extreme energy and transformation, essential for the ongoing cosmic cycle of element creation and stellar life. The 15 million degrees Celsius at its center represents the very crucible of creation, a silent forge where the universe builds its foundational elements. Our Sun is currently about 4.6 billion years old, a comfortably middle-aged star. Having traversed roughly half of its projected lifespan on what astronomers call the main sequence. The main sequence phase is the longest and most stable period in a star's life, a time when it is actively fusing hydrogen into helium in its core. For our Sun, this stable hydrogen-burning phase is expected to last for a total of approximately 10 billion years. This means that our Sun has already spent a significant portion of its life providing a steady, reliable source of light and warmth to Earth, allowing for the emergence and evolution of life. As a main sequence star, the Sun maintains a delicate balance between the inward pull of its own gravity, which constantly tries to compress it, and the outward pressure generated by the intense heat from its nuclear fusion reactions. This equilibrium ensures its consistent size and luminosity, providing the stable conditions necessary for planets like Earth to thrive. Knowing the Sun's age and its position on the main sequence gives us a quiet sense of its enduring reliability. A celestial clock that has ticked with unwavering precision for billions of years, and will continue to do so for billions more. It is a comforting thought, a quiet assurance of cosmic stability in an ever-changing universe, a steady beacon in the night sky. After its dramatic, yet gentle, red giant phase, the Sun will undertake another beautiful transformation, evolving into what astronomers call a planetary nebula. This stage is a relatively brief but visually stunning chapter in a star's life. As the red giant's outer layers expand and become increasingly tenuous, they are gradually, softly shed into the vastness of space, drifting away from the star's core. This process creates an expanding shell of glowing gas around the now exposed, extremely hot and compact stellar core. The intense ultraviolet radiation emanating from this remnant core ionizes the expelled gas, causing it to glow with a myriad of vibrant colors, forming intricate and often breathtaking shapes in the cosmic canvas. These celestial formations are known as planetary nebulae, a name that is somewhat misleading as they have no direct connection to planets themselves. The term arose from early telescopic observations that sometimes made them appear round and planet-like. The central core left behind will be a white dwarf, the dense hot ember of the Sun, quietly cooling over eons. The planetary nebula itself will expand and dissipate over tens of thousands of years, its beautiful ethereal glow gradually fading as its gases spread out and cool. This gentle dispersal of material serves a crucial cosmic purpose. It enriches the interstellar medium with newly created elements, providing the raw ingredients for future generations of stars and planetary systems. It is a quiet, artistic finale to a star's life, a beautiful, colorful exhalation that contributes to the ongoing cycle of cosmic creation and renewal, scattering its stardust back into the universe from which it came. The Sun's gravitational influence extends far beyond the familiar orbits of our 8 planets, reaching into the deepest, coldest, and most distant regions of our solar system. Its powerful, yet gentle gravitational pull defines the vast, spherical expanse known as the Oort cloud. This immense, theoretical cloud of icy planetesimals is believed to encircle our entire solar system, stretching outwards to distances that are thousands of times farther than the orbit of Pluto. Imagine a vast, ethereal shell of billions or even trillions of icy bodies, remnants from the early formation of our solar system, quietly orbiting the Sun at an almost unimaginable remove. The Oort cloud is thought to be the reservoir for long-period comets, those celestial wanderers that occasionally make a dramatic, luminous visit to the inner solar system before returning to their distant, dark abode. These comets are gently dislodged from the Oort cloud by the subtle gravitational tugs of passing stars or galactic tides, beginning their long, slow journey inward. The existence of the Oort cloud is a quiet testament to the immense reach of the Sun's gravity, a force that silently organizes and holds together a vast, unseen realm of icy bodies at the very fringes of our stellar neighborhood. It reminds us that our solar system is far larger and more complex than the familiar planetary orbits suggest. A quiet, extended family of objects, all bound by the subtle, enduring embrace of our star's gravitational field. This vast dark sphere is a silent, frozen archive of our solar system's birth, held gently in the sun's distant sway. Finally, our sun itself holds a specific place in the grand classification of stars. It is formally categorized as a G-type main sequence star, a designation that places it firmly within the most common and stable category of stars in the universe. While it is often colloquially referred to as a yellow dwarf, this term can be slightly misleading. From the pristine vacuum of space, the sun actually appears white. Its yellowish tint when viewed from Earth is a gentle optical illusion caused by the scattering of blue light by our planet's atmosphere, allowing more of the yellow and red wavelengths to reach our eyes. As a main sequence star, the sun is in the prime of its life, steadily and reliably converting hydrogen into helium in its core through nuclear fusion. This stable process ensures its consistent output of energy, which has been crucial for the development of life on Earth. G-type stars are known for their moderate temperatures, sizes, and luminosities, making them excellent candidates for hosting planetary systems capable of supporting life. Our sun is a quiet, dependable star, neither exceptionally large nor small, neither incredibly hot nor cold, but perfectly suited to its role as the stable heart of our solar system. Its classification speaks to its balanced and enduring nature, a steady, white-hot beacon in the cosmic night that has quietly sustained quiet order and gentle rhythm of stellar existence. The serene, balanced existence of our sun, while a testament to stellar stability, represents only one facet of the intricate and often surprisingly social lives of stars. Indeed, a significant number of stars in the cosmos do not journey through space alone. Instead, many are born in elegant partnerships, or even in graceful trios, locked in complex and enduring gravitational dances. These celestial pairings are known as binary or multiple star systems, and they are far more common than solitary stars like our sun. Imagine 2, or sometimes 3, luminous spheres tracing intricate, harmonious orbits around a common center of mass, their gravitational embrace binding them together for billions of years. These stellar companions can be quite close, their atmospheres almost touching, or they can be separated by vast distances, their orbits unfolding over millennia. Each star in such a system exerts a gentle, continuous gravitational pull on its partner, creating a beautiful, ceaseless ballet in the emptiness of space. This quiet, orbital synchronicity is a testament to the fundamental force of gravity, weaving together individual stars into larger, interconnected celestial families, each contributing to the subtle rhythms of the galaxy. Their shared journey through the cosmos is a long, patient dance, a testament to the universe's capacity for intricate, enduring relationships, a silent symphony of orbital precision. In some of these close-knit binary systems, the gravitational intimacy between the stars can lead to remarkable and gentle exchanges of material, a cosmic interaction sometimes referred to as stellar cannibalism, though it is a far more elegant and less dramatic process than the name suggests. As one of the stars in the pair evolves, perhaps expanding into a red giant, its outer layers can extend outwards, coming under the gentle gravitational influence of its companion. When this occurs, the companion star can begin to softly siphon off material from its larger partner. This flow of gas typically forms a beautiful, glowing accretion disk around the receiving star, a swirling vortex of matter being gently transferred. This steady, quiet transfer of mass can profoundly alter the evolutionary paths of both stars. The donor star may gradually lose a significant portion of its mass, revealing deeper, hotter layers, while the recipient star becomes more massive and luminous, potentially changing its classification and lifespan. Such delicate exchanges can lead to a wide array of fascinating stellar phenomena, from bright bursts of light to the eventual formation of exotic objects like white dwarfs or neutron stars. These interactions are not violent collisions, but rather slow, graceful dances of matter and gravity, a continuous, subtle reshaping of stellar destinies played out over millions of years, a quiet blending of their individual lives into a shared cosmic narrative. It is a profound example of how stars, in their quiet proximity, can mutually influence and redefine one another's existence. The presence of multiple stars in a system doesn't necessarily preclude the formation and stable existence of planets. Indeed, astronomers have discovered worlds that serenely orbit binary stars, creating the captivating spectacle of a sky adorned with two suns, much like the iconic fictional world of Tatooine. These are known as circumbinary planets, and their existence confirms the universe's boundless capacity for planetary diversity. Imagine a world where dawn brings not one, but two sunrises, painting the sky with a double palette of light and shadow. The orbital mechanics for such planets are understandably more intricate than those in our single-star solar system, yet they are remarkably stable, allowing these worlds to maintain their graceful paths around their dual parent stars. The gravitational forces from two stars create a complex but predictable environment, where a planet can find a stable orbit if it is sufficiently far from the stellar pair. These discoveries have expanded our understanding of where planets can form and thrive, gently pushing the boundaries of what we once considered possible. Worlds with two suns offer a quiet, beautiful vision of cosmic variation, reminding us that the familiar single-star system of our Earth is just one of many elegant arrangements that can arise in the vast cosmic tapestry, each offering a unique perspective on the interplay of light and gravity. The gentle, shifting glow from two stars would cast long, dancing shadows, creating a unique and tranquil rhythm of day and night. While many stars remain gravitationally bound within their birth clusters or binary systems, not all are destined for such communal journeys. Some stars embark on solitary paths, becoming quiet wanderers across the vastness of space, gently ejected from their stellar birthplaces. This often occurs in dense star clusters, where close encounters between multiple stars can lead to powerful gravitational interactions. In a cosmic dance of subtle pushes and pulls, a star can gain enough velocity from these interactions, much like a gravitational slingshot, to gently break free from the collective gravitational embrace of its cluster. Once ejected, these stars become unbound, silently drifting away from their stellar families, traversing the interstellar medium alone. They are like cosmic nomads, leaving behind the bustling stellar nurseries where they were born to embark on an independent journey through the quiet dark. These solitary wanderers, though less numerous than their clustered counterparts, are a testament to the dynamic and ever-changing nature of stellar environments, where even the most tightly bound groups can experience the gentle dispersal of their members. Their silent, unhurried passage through space is a poignant reminder of the universe's capacity for both connection and quiet solitude, each star tracing its own unique, unbound path through the cosmic expanse. Extending this idea further, there are also truly rogue stars that drift through galaxies, completely unattached to any specific star system or cluster. These are the ultimate cosmic loners, traversing the vast intergalactic void without the gravitational anchor of a parent star or a stellar family. Unlike stars gently ejected from clusters, these rogue stars might have formed in isolation, far from dense nebulae, or perhaps they were stripped from smaller, less stable systems that were disrupted by larger galactic forces. They move silently through the galaxy, their paths often taking them far from the luminous spiral arms, into the quieter, darker regions of the galactic halo, or even into the spaces between galaxies. Detecting these wandering stars is a subtle challenge for astronomers, as they are often dim and isolated, their presence revealed only by their faint light or their gentle gravitational influence on other objects. Their existence paints a picture of a dynamic cosmos, where not every star is part of a grand design or a discernible pattern. Instead, some simply drift, following their own quiet trajectories, silent, luminous points of light moving through an otherwise empty canvas. Each one is a testament to the universe's vastness, a quiet reminder that even in the grand tapestry of galaxies, there are individual threads that unravel and journey alone, tracing a path of quiet independence through the cosmic ocean. On an even grander scale of cosmic interaction, our own Milky Way galaxy is engaged in a profound and elegant celestial dance with its closest large galactic neighbor, the Andromeda Galaxy. These two immense spiral galaxies are currently on a slow, inexorable collision course, a gravitational embrace that will unfold over billions of years. At present, Andromeda is approximately 2.5 million light-years away from us, a significant but steadily closing gap. In about 4 billion years, the two galaxies will begin their graceful merge. However, it's a fascinating detail that the outer halos of both galaxies, which are vast, diffuse clouds of hot gas and dark matter extending far beyond their visible stellar disks, are already subtly overlapping. In this sense, the two colossal systems have already begun their gentle interaction, quietly touching across immense cosmic distances. The eventual merger will not be a catastrophic crash of stars, as the vast distances between individual stars mean that direct star-on-star collisions will be incredibly rare. Instead, it will be a slow, elegant blending, a graceful rearrangement of billions of stars, gas, and dust, over eons. The two distinct spiral shapes will gradually coalesce into one much larger, more elliptical galaxy. Astronomers have affectionately dubbed this future galactic entity Milkomeda, a quiet testament to the eventual union of these two majestic systems. This grand cosmic meeting is already in motion, a silent dance playing out over unimaginable timescales, a beautiful and inevitable transformation that will reshape our galactic neighborhood with quiet grace. This gentle merging of galaxies is a testament to the universe's continuous evolution, a silent, ongoing process of growth and transformation. It reminds us that even the largest structures in the cosmos are not static, but are constantly engaged in subtle interactions that reshape their forms and destinies. The gravitational pull between galaxies orchestrates these grand dances, leading to mergers that gradually build larger and more complex systems. The outer halos, those invisible envelopes of dark matter and sparse gas, are the first to encounter each other, initiating the long process of integration. This quiet initial overlap is a precursor to a more complete, yet still gentle blending of stellar populations and interstellar material. The stars themselves, rather than colliding, will mostly pass by one another, their individual orbits gently perturbed and redirected by the immense gravitational fields of the two merging galaxies. Over hundreds of millions of years, the familiar spiral arms will slowly unravel and reform, eventually settling into a new, more elliptical configuration. This transformation is a cosmic ballet of immense proportions, a slow, majestic unfolding that speaks to the universe's capacity for grand-scale, yet unhurried, change. The quiet, inexorable pull of gravity guides these colossal systems, transforming two distinct entities into a unified, larger whole, a silent testament to the enduring power of cosmic attraction. It is a future written in the gentle curves of space-time, a beautiful, inevitable resculpting of our galactic home. The quiet intertwining of these vast systems will be a long, serene process, culminating in a new, unified cosmic entity that will shine with a combined brilliance. This grand galactic evolution is a beautiful testament to a fundamental truth of stellar existence. A star's eventual fate is determined primarily by its initial mass. From the moment of its birth, the amount of material gathered by a forming star dictates its internal pressure, its core temperature, the types of nuclear fusion it can sustain, and ultimately, the elegant manner in which its life will conclude. Whether it gently fades over eons, swells into a luminous giant, or collapses into an incredibly dense remnant, or a profound black hole, every star's destiny is quietly inscribed within its mass at the very beginning of its luminous journey. This foundational principle shapes the entire narrative of stellar evolution, creating the diverse array of celestial objects we observe across the cosmos, each following its own predestined path, a quiet unfolding of cosmic physics. Among the most enduring and tranquil of all stellar inhabitants are the red dwarf stars. These diminutive celestial bodies represent the lower limit of what can truly be considered a star. Due to their modest mass, red dwarfs engage in nuclear fusion at an incredibly slow and remarkably efficient rate, conserving their hydrogen fuel with an almost unparalleled frugality. This measured consumption allows them to live for truly immense spans. Scientists estimate that red dwarfs can quietly burn their fuel for trillions of years, a timescale that stretches beyond our comprehension. While they emit only a dim, reddish light, their sheer longevity means they embers scattered throughout the cosmic night. They are the patient sentinels of the universe, offering a quiet, stable source of warmth and light for potential worlds for unimaginably long periods, a testament to the universe's capacity for gentle, enduring existence. Their quiet glow will persist long after more massive stars have faded, a steady, unwavering presence in the deepening cosmic twilight. In contrast, stars of medium mass, like our own Sun, follow a different, yet equally graceful, evolutionary path after their main sequence lives. The term red giant refers to a star that has exhausted its primary hydrogen fuel in its core and, in response, has expanded dramatically in size. This transition is a gentle, internal restructuring. With core hydrogen fusion ceasing, the core begins to contract under its own gravity, causing it to heat up. This increased core temperature then ignites hydrogen fusion in a shell surrounding the now inert helium core. The energy released from this shell fusion pushes the star's outer layers outward, causing them to swell to immense proportions and cool down, giving the star its characteristic reddish hue. A red giant can become hundreds of times larger than its original size, a luminous, expanded sphere gently shedding its outer layers into space. This phase is a temporary, yet beautiful transformation, marking a star's serene transition from its stable, hydrogen-burning life to its final, more compact forms. It is a slow, majestic exhalation of stellar material, quiet reshaping of its cosmic neighborhood. Following the red giant phase for low to medium mass stars, the outer layers continue to drift away, forming a beautiful, ethereal planetary nebula. What remains at the heart of this dispersing cloud is a white dwarf, a dense, hot remnant about the size of Earth, comparable to that of our Sun, compressed into an incredibly compact volume. The matter within a white dwarf is so dense that a single cubic centimeter would weigh several tons, a profound testament to the power of gravity. These celestial embers no longer generate energy through a process that takes billions, even trillions of years. Over these immense timescales, a white dwarf will gradually dim, its faint glow slowly fading until it becomes a hypothetical black dwarf, a cold, dark, and invisible remnant. Every white dwarf observed today is still quietly glowing, a luminous fossil gently cooling in the cosmic dark, a quiet, enduring monument to stellar transformation. For stars far more massive than our Sun, their end is a more dramatic, yet still profoundly natural process. When these colossal stars exhaust their fuel, their cores collapse inward with immense gravitational force. This collapse triggers a magnificent, final burst of radiance known as a supernova, scattering most of the star's outer layers into space. What remains at the heart of this cosmic exhalation is a neutron star, the superdense core left behind. These objects are incredibly compact, typically only about 20 kilometers in diameter, yet they contain the mass of 1.5 to 3 suns. The matter within a neutron star is so compressed that electrons and protons have merged into neutrons, creating a state of matter so dense that a single teaspoon of it would weigh billions of tons. Neutron stars are the densest objects in the universe, short of black holes, and represent a quiet, extreme state of matter, a silent, heavy memory of a star that once blazed with incredible power. Their existence is a testament to gravity's profound ability to reshape matter into its most compact and exotic forms, a quiet, enduring presence in the cosmic void. For the most massive stars, those at the absolute upper limits of stellar mass, the gravitational forces at play are so immense that even a neutron star cannot withstand the inward pull. When these stars conclude their lives, their cores collapse completely, leading to the formation of a black hole. A black hole is not an object in the traditional sense, but rather a region of space-time where gravity is so overwhelmingly strong that nothing, not even light, can escape its embrace once it crosses a boundary called the event horizon. These profound gravitational wells are often formed from the direct collapse of massive stars, where the star's core implodes without the outward burst of a supernova, simply vanishing from view. The gravity within a black hole warps space-time itself, creating a funnel-like distortion where all paths lead inward to a singularity, a point of infinite density. They are silent, invisible devourers of light and time, yet their presence is profoundly felt through their gravitational influence on surrounding matter and the gentle bending of light. Black holes are the ultimate expression of gravity's power, a quiet, profound mystery at the heart of the cosmos, representing the serene, ultimate end for the most colossal stars, a final, unobserved transformation into pure gravitational presence. Beyond the realm of true stars, there exists a fascinating category of celestial objects known as brown dwarfs, often affectionately referred to as failed stars. These enigmatic bodies occupy a transitional space between giant planets and small stars. They are too massive to be considered planets, yet they are too small to sustain stable nuclear fusion of hydrogen into helium in their cores, which is the defining characteristic of a true star. Brown dwarfs do generate some heat and light through gravitational contraction and the temporary fusion of deuterium, a heavier isotope of hydrogen. However, this process is not sustained for long. As they age, they slowly cool and dim, radiating mostly in the infrared part of the spectrum, making them difficult to detect. Their dim, quiet glow means they are often invisible to optical telescopes, appearing as faint smudges in the cosmic dark. Brown dwarfs are a testament to the subtle variations in cosmic formation, representing masses that fell just short of achieving full stellar ignition. They are quiet, enduring presences, slowly cooling embers in the galactic void, reminding us that the universe is filled with a spectrum of celestial bodies, each with its own gentle, unique story of formation and evolution, a quiet continuum between the largest planets and the smallest stars. Their presence adds a layer of subtle complexity to the stellar census, enriching our understanding of the diverse outcomes of cosmic birth. Beyond these grand galactic ballets, individual stars also exhibit a fascinating array of unique phenomena and quirks, revealing their dynamic and often subtle internal lives. One of the most intriguing discoveries is that stars can, in a manner of speaking, sing through their internal vibrations. This isn't sound as we perceive it in the vacuum of space, which carries no air to transmit sound waves. Instead, these are deep, slow pressure waves that ripple and resonate through the star's superheated plasma, much like seismic waves traveling through the Earth's interior. These internal oscillations cause the star's surface to gently pulse and subtly change shape. Scientists have developed a specialized field of study called asteroseismology, literally the seismology of stars, to detect and interpret these faint stellar vibrations. By meticulously observing tiny, almost imperceptible changes in a star's brightness or the gentle movements of its surface, astronomers can listen to these silent cosmic melodies. Each star possesses its own unique set of internal frequencies, a kind of gravitational fingerprint determined by its specific size, its intricate internal structure, and its current age. By carefully analyzing these stellar songs, scientists can peer deep inside stars, much like using ultrasound, to learn what is happening beneath their luminous exteriors. This provides invaluable insights into their density profiles, their internal rotation rates, and even the complex flow patterns of their hot gases. It is a quiet, profound form of cosmic echolocation, a way to gently hear the music of stars across immense light years, even if the grand symphony remains silent to human ears, a testament to the subtle, rhythmic life within each stellar body. Furthermore, not all stars maintain a constant, unwavering glow. Some celestial bodies appear to flicker or subtly change their brightness in rhythmic patterns, earning them the classification of variable stars. These stars pulse with a slow, captivating stellar rhythm, their luminosity gently waxing and waning over periods that can range from a few hours to many months or even years. This intrinsic variability is not due to external factors like eclipsing planets, but rather to dynamic processes occurring within the stars themselves. In many cases, these pulsations are caused by changes in the star's outer layers, where gases gently expand and cool, then slowly contract and heat up again in a continuous, graceful cycle. This delicate interplay of internal pressures and temperatures creates a steady, predictable beat. These rhythmic variations are remarkably consistent in many types of variable stars, making them invaluable celestial clocks for astronomers. By carefully observing their pulsation patterns and measuring the period of their brightening and dimming cycles, scientists can use them as cosmic yardsticks to determine immense distances across the universe. A single flicker, repeated over and over with quiet precision, can unlock the secrets of a star's true brightness and its exact position in the vast cosmic tapestry, allowing us to map the universe with a gentle, rhythmic guide. These stars are living, breathing beacons, quietly broadcasting information across the void. Stars also exhibit bursts of intense activity on their surfaces, known as stellar flares, which are powerful bursts of radiation. While our own sun produces solar flares, these events on other stars can sometimes be many times larger and significantly more energetic than anything observed from our sun. These flares are thought to be caused by the sudden, elegant reconnection of complex magnetic field lines within the star's atmosphere, releasing vast amounts of stored energy in an instant. This release manifests as a sudden, intense brightening across various wavelengths, including X-rays, ultraviolet light, and visible light. While these flares are powerful, they are a natural part of a star's magnetic activity, a gentle release of accumulated energy. For stars with orbiting planets, particularly those in close proximity, such flares could have profound implications for atmospheric chemistry and habitability, a quiet yet potent influence on their planetary companions. These bursts are a reminder of the subtle, yet immense magnetic forces at play on stellar surfaces, a continuous dynamic interplay that occasionally manifests in these radiant, though non-dramatic, exhalations of energy, contributing to the quiet, ceaseless activity of the cosmos. In a related phenomenon, stars can also have spots on their surfaces, analogous to the sunspots we observe on our own sun, but often on a much grander scale. These stellar spots are regions of intense magnetic activity, where the star's internal convection is inhibited, causing the surface temperature to drop slightly and appear darker than the surrounding areas. While sunspots on our sun are relatively modest in size, lasting for days or weeks, the spots on other stars can be many times larger and significantly more powerful, sometimes covering a substantial fraction of the star's visible surface. These immense stellar spots can cause noticeable, yet gentle variations in the star's overall brightness as they rotate into and out of view. They are quiet indicators of the star's deep magnetic dynamics and rotational characteristics. The presence and movement of these spots allow astronomers to study a star's rotation rate and the complex patterns of its magnetic field, offering a silent window into the star's hidden internal workings. These cosmic blemishes are not imperfections, but rather beautiful, natural expressions of a star's magnetic life, subtly influencing its radiant output with their quiet, shifting presence. Our sun, in particular, exhibits a predictable and gentle rhythm in its activity, marked by an approximately 11-year activity cycle. This cycle is characterized by a gradual rise and fall in the number of sunspots visible on its surface, as well as a corresponding increase and decrease in the frequency and intensity of solar flares and other energetic events. During the peak of the cycle, known as solar maximum, the sun is adorned with numerous sunspots, and solar flares are more common and powerful. Conversely, during solar minimum, the sun's face appears relatively calm and unblemished, with fewer sunspots and less frequent flaring. This 11-year rhythm is intrinsically linked to the sun's magnetic field, which undergoes a graceful reversal of its polarity at the peak of each cycle. This predictable, yet profound, magnetic dance ensures a continuous quiet variation in the sun's output, subtly influencing space weather around Earth. The sun's activity cycle is a testament to its internal stability and its gentle, long-term predictability, a silent, rhythmic breathing that has persisted for billions of years, providing a steady, reliable rhythm to our solar system. It is a quiet, internal clock, marking the passage of stellar time with unwavering precision. Contrary to the idealized images often depicted, stars are not perfectly spherical celestial bodies. Their rapid rotation causes a slight, yet measurable bulge at their equator, giving them an oblate spheroid shape, much like a gently flattened sphere. This subtle distortion is a direct consequence of centrifugal force, the outward push generated by the star's spin. As a star rotates, the material at its equator experiences a greater outward force than the material at its poles, causing it to gently spread outwards. The faster a star spins, the more pronounced this equatorial bulge becomes, while for a relatively slow rotating star like our Sun, this flattening is barely perceptible. For very rapidly rotating stars, the effect can be quite dramatic, making them visibly wider at their middle than they are tall. This gentle reshaping of a star's form is a beautiful illustration of the interplay between gravity, which pulls matter inward, and rotational forces, which push it outward. It is a quiet, elegant testament to the dynamic nature of celestial mechanics, revealing that even the most massive and seemingly perfect objects in the universe are subtly molded by the forces that govern their existence, forever dancing between perfect form and the gentle distortions of motion. Finally, stars can also experience phenomena akin to starquakes, which are sudden, gentle shifts in their internal structure that cause subtle vibrations and observable changes in their brightness. These internal adjustments are not violent ruptures, but rather quiet releases of accumulated stress within the star's layers, perhaps due to changes in convection, magnetic fields, or the gradual settling of its dense core. When a starquake occurs, it sends ripples of pressure and motion through the star's interior, similar to how an earthquake sends seismic waves through Earth. These vibrations can cause the star's surface to subtly oscillate, leading to small, temporary variations in its luminosity that astronomers can detect with sensitive instruments. Studying these starquakes, often through the techniques of asteroseismology, provides invaluable insights into the star's internal composition, its density profiles, and the dynamics of its deep interior. They are like quiet murmurs from within, revealing the hidden life and subtle transformations occurring deep beneath a star's radiant surface. These gentle tremors are a reminder that stars, though seemingly stable, are dynamic systems, constantly making small, internal adjustments as they gracefully age, their quiet vibrations echoing across the vastness of space, a silent communication from the heart of a distant sun. This internal life of stars, however, is often perceived through a filter of immense cosmic distance and the subtle distortions of perception, revealing a complex interplay of light, time, and the very fabric of space. One of the most profound aspects of observing the cosmos is the understanding that the light from some stars we behold tonight left them billions of years ago, offering us an unparalleled glimpse into the cosmic past. When we gaze at a distant galaxy, or even a star far within our own Milky Way, we are not seeing it as it exists in this very moment. Instead, we are looking back in time, witnessing light that embarked on its journey across the vast expanse of the universe untold ages ago. Imagine the light from a faraway stellar nursery where new stars are gently igniting, beginning its long voyage across expanding space. That light may have traveled for 5 billion, 8 billion, or even 10 billion years before finally reaching our telescopes or our eyes. This means we are seeing those celestial objects as they were when the universe was significantly younger, perhaps before our own sun was born, or even before Earth had fully formed. Each photon that touches our retina or activates a sensor on a telescope carries with it a silent, ancient story, a frozen snapshot of a moment in cosmic history. This phenomenon transforms every deep sky image into a kind of time machine, allowing astronomers to quietly piece together the evolutionary narrative of the universe, observing galaxies in their infancy and stars in their earliest, most energetic phases. It is a humbling realization, a gentle reminder that the night sky is not a static canvas, but a living archive of time, where the past continually unfolds before our very eyes, a quiet echo from the universe's long and graceful journey. The sheer scale of these light travel times underscores the immense distances involved, making each distant pinpoint of light a profound connection to an ancient, vanished epoch, a silent whisper from the dawn of creation, softly arriving across unimaginable stretches of space. Paradoxically, the beautiful twinkling effect we often observe when looking at stars is not an inherent property of the stars themselves, but rather a gentle distortion caused by Earth's own atmosphere. Stars are, in fact, steady, unwavering beacons of light, emitting a continuous glow. The shimmering, dancing appearance we perceive is due to the constant movement and varying densities of air in our planet's atmosphere. Different layers of air with slightly different temperatures and pressures act like tiny, shifting lenses, gently bending and refocusing the starlight as it travels towards our eyes. As these atmospheric pockets move and churn, the path of the starlight is subtly altered, causing the star's apparent brightness and position to flicker rapidly. This effect is known as atmospheric turbulence. Planets, by contrast, appear much steadier in the night sky because they are significantly closer to Earth and thus present a larger apparent disk. Light from a planet arrives at our eyes as a bundle of many parallel rays, which are less susceptible to the individual distortions of atmospheric turbulence. The effects tend to average out, resulting in a more constant, gentle glow. So, while the twinkling of a star adds a touch of ethereal beauty to the night, it is a purely terrestrial phenomenon. A quiet dance between ancient starlight and our planet's ever-moving envelope of air, a beautiful illusion woven by the gentle breezes and thermal currents high above us, a testament to the subtle interaction between the cosmos and our immediate surroundings. The star itself, far beyond, remains a constant, serene source of light, unperturbed by the atmospheric ballet that transforms its distant glow into a shimmering jewel. Bringing this concept of light travel time closer to home, the light from our own sun takes approximately 8 minutes to reach Earth, traveling at the universe's ultimate speed limit, the speed of light. This means that when you look at the sun, you are seeing it as it was 8 minutes and 20 seconds ago, a tiny yet significant delay in cosmic communication. If, by some unimaginable event, the sun were to suddenly and silently vanish from existence, we would not know about it for another 8 minutes, as its final rays of light would continue their journey across the 93 million miles separating us, gently illuminating our world before darkness finally descended. This 8-minute journey is a fundamental constant in our solar system, a quiet reminder of the finite speed at which information can travel through space. It highlights the profound interconnectedness of our planet with its parent star, a continuous flow of energy that sustains all life, yet always with that subtle, inherent delay. This gentle lag in light's journey underscores the vast, quiet distances even within our own cosmic neighborhood, a constant, unhurried passage of radiant energy that shapes our days and nights, a testament to the steady, unyielding rhythm of the cosmos, where even the most immediate light takes its own measured time to arrive. To bridge these immense cosmic distances, astronomers use a specialized unit of measurement, the light year. It is crucial to remember that the term light year is a measure of distance, not of time, despite its evocative name. It represents the staggering distance that light, traveling at its constant speed of approximately 300,000 kilometers per second, can cover in a single Earth year. To put this into perspective, 1 light year is equivalent to about 9.5 trillion kilometers, or approximately 6 trillion miles. This immense unit helps us to quietly comprehend the truly vast scales of interstellar and intergalactic space. Without such a measure, the numbers required to describe the distances between stars and galaxies would become unwieldy and almost meaningless. For instance, the nearest star system to our Sun, Alpha Centauri, is about 4.37 light-years away, meaning the light we see from it today began its journey over 4 years ago. Galaxies, on the other hand, can be millions or even billions of light-years distant, each light-year marking another step across the silent, expanding canvas of the universe. The light year serves as a gentle cosmic ruler, allowing us to map the immense emptiness between celestial objects and to quietly appreciate the truly vast and sprawling nature of our universe, where even light, the fastest thing we know, takes eons to traverse the silent, boundless distances. Measuring these incredible distances requires ingenious methods. And for relatively nearby stars, astronomers employ a technique called stellar parallax. This concept is based on a simple geometric principle. As Earth gracefully orbits the Sun, our vantage point in space subtly changes over the course of 6 months. By observing a nearby star from 2 different positions in Earth's orbit, separated by approximately 300 million kilometers, astronomers can detect a tiny, apparent shift in the star's position against the backdrop of much more distant, seemingly fixed background stars. Imagine holding your finger out at arm's length and alternately closing one eye and then the other. Your finger appears to shift against the distant wall. Stellar parallax works on the same principle, but on a cosmic scale. The angle of this minute shift, known as the parallax angle, is inversely proportional to the star's distance. The smaller the angle, the farther away the star. This method allows for remarkably precise measurements of distances to stars within a few hundred light-years of Earth. It is a quiet triumph of geometry and observation, transforming the Earth's annual journey around the Sun into a cosmic baseline for measuring the depths of space, providing a fundamental rung on the ladder of cosmic distances and allowing us to gently map our immediate stellar neighborhood with quiet precision. Beyond the visible light that our eyes can perceive, stars are truly multifaceted emitters, radiating energy across the entire electromagnetic spectrum. Visible light, the familiar hues of a rainbow, constitutes only a tiny fraction of the total energy a star releases. Stars also gently emit X-rays. Ultraviolet light, infrared radiation, radio waves, and gamma rays. Each of these different wavelengths carries unique information about the star's properties and processes. X-rays, for example, often originate from extremely hot regions, such as a star's corona, the superheated outer atmosphere, or from the violent interactions in binary systems. Ultraviolet light comes from energetic processes in a star's upper atmosphere. Infrared radiation, by contrast, is often associated with cooler regions, such as dust clouds surrounding young stars or the faint glow of brown dwarfs. Radio waves can be emitted by complex magnetic fields or by the rapid rotation of neutron stars. To capture this full, rich spectrum of stellar emission, astronomers must utilize a variety of specialized telescopes, many of which are located in space, beyond Earth's absorbing atmosphere. By studying a star's light across all these wavelengths, scientists can piece together a much more complete and nuanced understanding of its internal workings, its surface activity, and its interactions with its environment. It is a silent, continuous broadcast of information, a gentle symphony of radiation that reveals the hidden life and profound complexity of stars, extending our perception far beyond the limits of human vision, allowing us to quietly listen to the universe's full range of silent frequencies. In a truly remarkable interplay of light and shadow, some stars appear to blink with a gentle rhythmic dimming when an exoplanet passes directly in front of them from our vantage point. This event is known as a transit, and it has become one of the most successful methods for detecting planets orbiting other stars. When an exoplanet crosses the face of its host star, it briefly blocks a tiny fraction of the star's light, causing a subtle, temporary dip in the star's observed brightness. This gentle dimming is usually very small, often less than 1% of the star's total light, requiring incredibly sensitive instruments to detect. However, if this dimming recurs at regular intervals, it provides compelling evidence for the presence of an orbiting planet. The duration of the transit, the depth of the dimming, and the frequency of these blinks can all provide valuable information about the exoplanet's size, its orbital period, and even its atmospheric composition. This quiet, repetitive signal has allowed astronomers to discover thousands of exoplanets, revealing a vast and diverse population of worlds beyond our solar system. Each gentle blink of a distant star is a silent confirmation of a hidden world, a subtle celestial announcement that another planet is tracing its quiet path around a faraway sun, a testament to the universe's endless capacity for planetary systems, each one a tiny, elegant interruption in the steady flow of starlight. The universe, in its boundless capacity for intricate arrangements, presents us with not only individual stellar dramas and planetary revelations, but also the grand, sweeping narratives of stellar populations and their collective structures. It is a quiet testament to the ever-evolving nature of galaxies that some stars are, in fact, older than the very galaxies they currently call home. This fascinating phenomenon arises from the slow, elegant process of galactic growth, where larger galaxies gradually coalesce and expand by gently merging with smaller, less massive systems. Imagine a grand cosmic dance unfolding over billions of years, where countless smaller stellar islands are softly drawn into the gravitational embrace of a larger spiral or elliptical system. During these graceful mergers, the stars that once belonged to the smaller absorbed galaxies continue their individual journeys, now integrated into the fabric of their new, larger host. These ancient traveler stars, having witnessed the birth and demise of their original galactic homes, carry with them the quiet memory of a different cosmic era. They are often found in the outer halos of galaxies or in streams of stars that bear the indelible, subtle mark of their past origins. Their chemical compositions might subtly differ from the stars born within the larger galaxy, offering astronomers a quiet, invaluable clue to their ancient heritage. These stellar elders float serenely through their adopted homes, silent survivors of earlier cosmic encounters, their light a soft echo from a time when the universe was structured differently, a testament to the continuous, gentle reshaping of galactic landscapes. Their presence reminds us that galaxies are not static, unchanging entities, but rather dynamic, living systems that grow and evolve through a long, patient process of accretion and integration, slowly weaving together the stellar tapestries of the cosmos. Each of these ancient stars is a quiet, luminous fossil, preserving a fragment of an earlier, vanished epoch, a gentle whisper of galactic ancestry carried across immense spans of space and time. They are the quiet witnesses to the universe's ceaseless, elegant transformation, their enduring light a beacon of cosmic history. Within the vast, quiet expanse surrounding galaxies, there exist some of the most venerable and awe-inspiring stellar structures known, globular clusters. These are ancient, densely packed groups of stars, often containing hundreds of thousands, or even millions, of individual suns, all gravitationally bound into a single, majestic, spherical ball. Unlike the stars in the main disk of a galaxy, which typically orbit in a flat plane, globular clusters trace long, sweeping paths through the galactic halo, a vast, diffuse sphere of gas and dark matter that envelops the visible galaxy. These clusters are among the oldest objects in the universe, with many of their stars being nearly as old as the cosmos itself, often 13 billion years or more. Their stars are typically metal poor, meaning they contain very few elements heavier than hydrogen and helium, a quiet indication of their ancient origins from the early universe. The immense gravitational pull within a globular cluster means that its stars are incredibly tightly packed, particularly towards the center, creating a shimmering, luminous core where stars are far closer to each other than in our own stellar neighborhood. Despite their density, these clusters are remarkably stable, enduring for billions of years as silent, majestic satellites, gracefully orbiting their host galaxies. Each globular cluster is a quiet, self-contained universe of ancient light, a shimmering ball of stellar history, providing astronomers with invaluable insights into the early formation and evolution of galaxies. They are like quiet, living museums of the cosmos, preserving a pristine sample of the universe's earliest stellar populations. Their collective glow, a soft, enduring beacon from the dawn of time, a testament to the beautiful, enduring power of gravity to bind countless stars into a harmonious, ancient whole, tracing their patient, silent orbits through the galactic night. In gentle contrast to the ancient, tightly bound globular clusters, we find the more youthful and loosely arranged groupings of stars known as open clusters. These stellar nurseries are typically found within the spiral arms of galaxies, the very regions where new stars are actively and quietly forming from collapsing clouds of gas and dust. Open clusters usually contain a few hundred to a few thousand stars, a more modest population compared to their globular counterparts. The stars within an open cluster are relatively young, often having formed at roughly the same time from the same initial nebula, making them stellar siblings that share a common origin. Unlike globular clusters, which are held together by immense gravity for billions of years, open clusters are more transient and less densely packed. Their gravitational bonds are weaker, and over time, they slowly disperse as their member stars gently drift apart due to gravitational interactions with other stars, gas clouds, and the broader tidal forces of the galaxy. This dispersal is a slow, elegant process, a gradual unbinding of stellar families as they embark on their individual journeys through the galactic disk. Open clusters appear as beautiful, glittering collections of young, bright stars, often still nestled within the wisps of the gas and dust from which they were born. They serve as quiet indicators of ongoing star formation, luminous signposts marking regions where the universe is actively, yet gently, renewing itself, creating new generations of suns to illuminate the cosmic night. Their existence is a graceful, fleeting chapter in stellar evolution, a quiet testament to the continuous cycle of birth, growth, and gentle dispersal that shapes the stellar populations of the galaxy. Shifting our perspective from individual stars and clusters to the grander architecture of the cosmos, it becomes clear that stars are not evenly distributed throughout space. Instead, they exhibit a profound tendency to gather together, forming the immense luminous structures we call galaxies. These galaxies, in turn, are not scattered randomly, but arrange themselves into even larger, intricate patterns, forming what astronomers refer to as the cosmic web. This observation underscores a fundamental principle of cosmic organization. Gravity, acting over immense timescales, gently sculpts the raw material of the universe into these beautiful, hierarchical structures. From the smallest dwarf galaxies to the most majestic spirals and ellipticals, stars are the luminous building blocks, quietly congregating in their billions and trillions. Each galaxy is a distinct island of stars, gas, and dust, a self-contained celestial city. Yet each is also part of a larger, interconnected network. The clustering of stars into galaxies is a quiet, elegant consequence of the universe's initial conditions, and the ceaseless pull of gravity, transforming a seemingly chaotic distribution of matter into an ordered, breathtaking tapestry of light. These vast cosmic structures, visible across billions of light years, are organization, a quiet, intricate weaving of light and matter into a grand, observable design, a beautiful, evolving architecture that spans the entirety of creation. Each galaxy, a silent beacon in the cosmic dark. Our own home, the Milky Way, is a prime example of such a magnificent galactic structure, a vast spiral island teeming with an almost unimaginable number of stars. Scientists estimate that the Milky Way contains anywhere from about 100 billion to 400 billion stars, each one a luminous furnace, quietly contributing to the galaxy's overall glow. This immense population includes a diverse array of stellar types, from the long-lived dim red dwarfs to the brilliant short-lived blue giants, and countless stars like our Sun, each following its own unique evolutionary path. These stars are arranged in a majestic spiral pattern, with luminous arms gently coiling around a central bulge, at the heart of which lies a supermassive black hole. The sheer number of stars within our galaxy is difficult to fully comprehend, representing a staggering collection of individual suns, each with its own story, its own potential planetary systems, and its own place in the grand galactic ballet. Despite this immense number, the distances between individual stars are so vast that our galaxy appears mostly empty, a quiet testament to the scale of interstellar space. The Milky Way is a dynamic and evolving system, its stars slowly orbiting the galactic center, creating a continuous, gentle flow of light and motion. It is our cosmic home, a vast, luminous tapestry woven from billions of individual suns, each a quiet, enduring light in the endless night, a constant source of wonder and discovery, inviting us to contemplate the sheer abundance of stellar existence. And when we extend our gaze even further, beyond the comforting confines of our own galaxy, to encompass the entirety of the observable universe, the numbers become truly mind-boggling. The total number of stars in this vast, visible cosmic expanse is estimated to be around 1 sextillion. To write that number out, it is a 1 followed by 21 zeros, 100 billion trillion stars. This astonishing figure represents an almost incomprehensible collection of luminous bodies, each a miniature universe of fusion and light, scattered across billions of galaxies and an even greater expanse of space. This estimate, however, applies only to the observable universe, the portion of the cosmos from which light has had sufficient time to reach us since the Big Bang. Beyond this cosmic horizon, the universe undoubtedly continues, stretching into regions that remain forever beyond our current perception, potentially containing an infinite number of additional stars and galaxies. The sheer scale of stellar existence within just the observable universe is a profound testament to the universe's boundless capacity for creation, a quiet, continuous process of igniting and sustaining countless luminous points of light. Each one of these sextillion stars contributes to the overall radiance of the cosmos, a collective glow that illuminates the vast darkness, a silent, countless chorus of celestial fires. This immense, uncountable multitude of stars paints a picture of a universe that is rich, vibrant, and filled with an almost infinite array of wonders. Each star, a quiet, enduring beacon in the grand unfolding narrative of cosmic existence, a testament to the profound abundance of light in the universe. As we gently close our exploration of stars, contemplating the 1 sextillion luminous beacons scattered across the observable cosmos, we are left with a quiet sense of the universe's infinite wonder and its profound, gentle rhythm. Imagine each star, a distant ember, a silent heart beating across the eons, contributing its soft glow to the cosmic tapestry. Feel the quiet drift through nebulae where new suns are slowly forming, or the serene, enduring dance of ancient galaxies. The universe is a place of ceaseless motion, yet also of profound stillness, holding both the fiery birth of stars and the long, slow fade into cosmic twilight. It is a space where light travels for billions of years, carrying ancient stories, and where even the vacuum hums with unseen quantum whispers. May this journey through the quiet wonders of the stars allow your own thoughts to soften, your breath to deepen, and your body to find a gentle rest. May your dreams tonight be as vast and peaceful as the cosmos itself, filled with the quiet beauty of distant starlight. Sleep gently now, knowing you are a part of this magnificent silent dance.